Problem 1.8. Here we are asked to find the potential energy function V of a system described by the state function psi, which is a function of both x and t. So this is the state function, and A, B are constants. M is the particle's mass. And all we need to do is find the potential energy function for the system. So the easiest way to do this is to solve the Schrodinger equation, right? So the Schrodinger equation is very simple. I would say it's just better to memorize it because it's the foundation of quantum chemistry, right? So it's I h bar times del is equal to negative h bar square by 2m times the second derivative of the state function with respect to the x coordinate. So this is a Schrodinger equation. So this is something we must remember. Now, as we can clearly see, the state function that we have is easily separable into a time-dependent portion and an x-coordinate dependent portion. So it can basically be written in the form of a function of time minus a function of x, where f of t would be a times e to the negative ibt, and this would be the other exponential term. You can also bring the constant to the x-dependent part. I just chose to put it in the time-dependent part. You can always bring it to the other side. I mean, it's just a constant, so it's not really going to matter which portion of the terms you want to put it in. It doesn't really matter. So when we have a wave function that can be clearly separated, that can be clearly separated into a time-dependent and a coordinate-dependent function, then the Schrodinger equation can be simplified, right? So if we were to divide this entire equation by psi, by the state function, actually, before we even do that, let me just write it out. Because we have a derivative with respect to time and not the x coordinate, the psi of x of the wave function is going to come out because that will just be a constant with respect to time. And instead of using partial derivatives, we can actually use the regular derivatives. This will be, and here the function of time can come out because we only care about how the state function changes with x. So what I did in this equation was I basically just wrote the state function in this form everywhere. And I took the constant part, like when we are taking the derivative with respect to time, the function of the coordinate is going to be a constant. So that's going to come out of the derivative and so on. So I basically just tried to simplify the equation. And now what I'm going to do is I'm just going to divide the entire equation. Use a different color to show how it looks like. with f of t and psi of x. So if I were to divide this with f of t and psi of x, this with f of t and psi of x, f of t and psi of x. So now that I have, this is permissible because I'm dividing both sides of the equation with the same term, so that can be done. High school algebra. Now I'm going to cancel out the terms that get canceled out. Now this will give us IH bar over f of t, df of t by dt will be equal to this. Now, all we care about is finding out the value of the potential energy function, right? So before we find the value of that, there are some things we need to solve. One is we need to take the derivatives with respect to time, and the second derivative with respect to the x coordinate. So before we do anything, let's first take the derivative with respect to the time. That seems to be the simpler thing to do. So df of t by dt would be, what is our time function? It's this. It's going to be e to the negative I. So the constant comes out of the derivative, and the derivative of an exponential is the exponential times negative IB, because you take the derivative of negative IBT with respect to t, that will give you this. So you can write it as negative I, A, B, E to the negative IBT. So we have the derivative with respect to time. Now, now that we have the first derivative with respect to time taken, let's work with the second derivative of the x coordinate function. That would be, before we go to the second derivative, why don't we just do the first derivative? The first derivative of this function would be the exponential times, we need to take the derivative of what is in the power, right? And that would be this. So I can bring all the constants aside. Say, so this is the first derivative. Now that we have the first derivative, let's take a look at the second derivative. So the second derivative would be, we're just taking a derivative of the first derivative. That shouldn't be that bad. However, we have two terms that are dependent on x. So we have to use the differentiation of a product rule. So let's first differentiate the exponential term. So we can have this term taken out separately, and we're going to differentiate the exponential term, which is exactly what we did in the first derivative. So the answer would exactly be what we had in the first derivative, that is this. Now, I'm going to bring the constant here. We're going to do apply the product rule for differentiation, right? So when we differentiate only the x, it's just going to be 1. So everything else would remain as it is. We're just differentiating the x. Now the second derivative could be simplified. So I can take some terms in common. So the negative and the negative will give you a positive. So I'm going to take 2bn by h bar. That's something that can be taken out of both the terms times I can have 2bn by h bar. Sorry, let me, I can take out 2bn by h bar, and I can also take out the exponential term common. Now I can have 2bn by h bar times x squared. You have an x and an x, so you have an x squared minus 1. So I have the second derivative to be something like this. Maybe I can simplify this a little bit. So we have 2bn by, doesn't seem to be enough place. I'm just going to do 2bn by h bar times e to the negative bn x squared by h bar times 2bn x squared minus h bar divided by h bar. Now this can be simplified, and I can actually combine the h bar and the denominator here to give us this term. So this is a second derivative of the function that depends only on the x coordinate. After solving for the first derivative with respect to time and the second derivative with respect to x, let's go back to the Schrodinger equation. We can write it as IH bar times f of t. You can refer to the previous a few minutes away before, where we actually showed what the equation would be. The IH bar divided by a, the negative t, that's f of t, times the derivative of f of t is here, which is this. Now this will be equal to negative h bar squared over 2n times 1 over e to the negative bn x squared by h bar times the second derivative of x squared, which is right here. This multiplied by 2bn h bar squared. Sorry, not h bar squared, 2bn x squared minus h bar. Plus, we have the x comma t. That's what we are supposed to find. Now, this is the best part. We're going to have a bunch of cancellations going on here. A gets canceled, this gets canceled. I squared is a negative 1, and we also have a negative here. So negative I squared is just going to be 1. So after those beautiful cancellations, here we have BH bar. So here, right hand side, BH bar equals. Well, let's go to the cancellations again. The 2m gets cancelled. H bar squared gets cancelled. The exponential term gets cancelled. So once those beautiful calculations are done, we are left with negative, it's just the b that remains, right? Negative b times 2bn x squared minus h bar plus v of x bar. Now I can write the same thing as 2b squared and x squared plus bh bar, 3 of x bar. Here we have another beautiful cancellation, and this implies v of x comma t is 2b squared and x squared, or you can write as 2m b squared x squared. And this is what we are supposed to find. So this is the answer.